So, we've now ended up with the final pre-lecture of our series, where we're going to discuss a few of the advanced topics that we haven't covered. It may not surprise you that it's probably a large fraction of the language, because what we've really concentrated on is the basic ideas. We haven't really gone in depth on any topic. You may all feel like you have, but we haven't, trust me. So, one of the key features of many of the modern languages that they are often supported by a rich library of functions and classes. For C++, that's called the standard library. And we've already made use of substantial parts of that. Things like IOStream, FStream, IO manipulations, strings, vectors, and all kinds of other objects that come. So standard library routines are declared in the std : namespace. But we can basically split into four sections. There's the standard library, there's the standard template library, the IOStream libraries, and miscellaneous libraries. On top of that, many of us often use the Boost library, which is truly enormous and very useful in many cases. And much what was in Boost actually ends up in the C++ library. But I won't discuss Boost very much because Boost you're not allowed to use Boost for your final project. So essentially, I better not discuss that in any detail. But if you really want to become a serious C++ programmer, then understanding what is in Boost is quite helpful as well. So let's talk a little bit about the standard library. The C standard library was really what influenced the idea from C++. Initially, C++ was considered a superset of C, so there was no need to rewrite some useful functions which are in C math, and some of them have ended up in the string. Now, C math is a debatable one because essentially there's a big difference between the C math library and a C++ math library, which doesn't exist but is supposed to come into being in a newer version of C++. It would be really nice if pi, for example, was built into the C++ library rather than having it the clumsy way to get to mpi from C math in various different compilers. So there's the standard template library, which is a useful set of template classes. For example, you can have container classes, which are standardized data structures such as the vector, the list, queue, dequeue, map, set, etc. Then there's algorithms: copy, find, sort, reverse, but there's a whole lot of them. The idea of iterators. So it makes it really useful to change data structures without having to change the way to run through them. And there are numeric ones as well, not probably as much as physicists would like, but complex is a key example of that. The IOStream library, which is clearly the one we've used quite a bit of, is the OStream and FStream parts of it. And there's miscellaneous libraries like the string and utility and lots of other of them. So for example, if you look at the reference I give you over here, and I would suggest you do that, then you can actually see much more details of how this actually works, and you can actually see how many parts of that standard library there are. Full details are really beyond the scope of this course, so I will provide you with a few examples, some of which we've already covered, but I'll try to put them in a slightly different context just so you understand what goes on over there. Okay. For example, complex numbers. I mean, I force you to write complex numbers, but of course C++ already provides one. And I have to apologize for making you do something that C++ already has. I mean, that's clearly not necessarily the optimal practice, but it does work. So let's work our way through some of that. It's called a class template. Okay, so it is a template which takes a class as an argument, which is typically specialized for float double and long double. So you get a template class T, class complex, so you can do all the stuff we've already done before, doubles, add and multiply them, take real parts, imaginary parts, arguments, and a modulus, and essentially that all exists. And there's many books that will discuss further information on these things. Another one that's really useful is the idea of pairs. It's a useful class when you have a close association of two object types. So that, for example, a double and a string always combine in some way or form. It's defined in the utility library, and the example is that a pair could contain a double and a string. So that would be an object one that contains a double and a string, and I can set the first one to 1, and then you can play with that. It could be used for the map class, as we see later, which is actually uses an implementation of pairs to do these kind of things. Now, the most important part of the standard template library, as I see it, is the idea of container classes. So they're objects that designed many objects within a single container. And you can really put these in 3 different places. One of them is a sequence container, like a vector, where all the objects come in order, a list, where it also happens, a D queue, which is D means double-ended queue, where essentially to get to any element of the list, it's linear in the number of elements in the list. So the time it takes is linear. There's associative containers. They are elements with a key, set, multiset, map, multi-bit set. It often is harder to get to an element, so it takes slightly longer. And container adapters, they provide a specific interface for some of the above, which is, for example, a queue, but I won't discuss container adapters. And as soon as C++ standard changes, which is every 3 years, there's usually many, many more, and at this point I'm probably lost to see what all of them are. Elements of container classes are accessed using iterators normally, but let us look at a few examples. We've already met vector, which was a dynamic array. Vectors allocate contiguous memory, which means you can random access. There's a strict linear relation between the element and its memory address, like there's in an array, right? When you erase, the elements all go one after another. Another sequence container is the list, where each element instead uses 2 pointers, which actually means for a list I can always work out what the previous and the next element is. But if I really want an element that's 10 steps away, I really need to take the 10 steps in turn by using those pointers to get to that element. And lists are useful because they're faster than vectors if you want to add an element, remove elements, or organizing elements, which is sorting. More awkward to find individual elements, right? Essentially, you must use an iterator or even the search algorithm, and the search time will be substantially longer. And one of the things about algorithms is often their complexity, which is given the time listed a number of elements. But that might be, if you want to know more about algorithms, you really should look it up. So let's look at an example over here. I've got a simple thing that uses list. This prints a list, okay, so it iterates over a list and essentially outputs all the elements in them. Then I've got a main program which has a list and I can push to the front or push to the back. That's the useful part of a list. You can either add on one side or the other side of the list. And then I can actually identify the elements by writing an iterator. In this case, I've been rather explicit. My list of begin, I can actually iterate over these things. I can insert. I do various things to this thing. Print list, my list dot sort, print list, my list, and you can see what happens. So the print list is actually the important function I've defined over there, and you can pop the front and the backs and stuff like that. You can even merge lists or combine 2 lists together, which is quite useful to do, and then sort them. So essentially, for example, the initial one is the 2, 1. So I added 1 first and 2 at the front, 3, 4 at the back. Then I inserted 5 in the middle. I just added another list. I concatenated those 2 lists and then sorted them. And then I can delete elements so this is the insert. 3 is after the sorting of the list. 4 is the second list. Is the new merge list, and then sorted, and 6 new lists with first and last element deleted. So there's various useful operations you can do, and hopefully if you write a code, you want to think, well, essentially, what are the type of operations I want that really determines the data structure that you're going to use, the type of container you're going to use for your data. Associative containers are quite interesting. Many of you may have seen dicts in Python. It's similar to that. In this case, it's the map class, which is a template class, which takes a pair of object types, a key and the data. And the trick is it overloads the square bracket operator to use a key instead of a position in an array. So it actually will do a type of search. It's a useful method for accessing textual information stored with a key, which is actually a very naive idea of a database. It's not a very good database, but it definitely works as a database. And the idea of storing the data in a given way, I mean, you may want to look up what a B tree or B prime tree is if you're really interested in the type of algorithms. It's often used in databases as well to search through things quickly. And the argument is, if you look over here, you include a string, a utility map. You define a map which has commands a string and international dial codes, right? That's a map. You've got an integer, a string, and that would be international dial codes for country. And I write a search database function that essentially iterates through this thing and then finds actually it searches for a given code in the list, and of course it then checks where it ends up at the end, finds an entry for the dial code, else standard error code is not in the database. So okay, so this actually searches for a code. Then I can send some sensible international dial codes like the one for Germany and the UK, or the one for Christmas Island, which is because it's a 3-digit dial code. You can actually look at the size of the database. You can then iterate them. You can print out, of course, all dial codes. You can search for 672, which we know is in there, or you can search for 673, which we know is not in there, and that's perfectly okay, right? Essentially, this looks like a very nice standard code, and this code's output, the size of the database is 3, dial codes in there, and it finds the one for 672 and gives me no information for 673 because it's not in there. Now, map actually, intriguing enough, requires an order. So that really means if you have a key, then you need to define a comparison operator, which is in this case the less than operator, must be defined for the key data type. So essentially, if you define your own class as the first element, right, as the key, then you need to be able sure that you've got a sort operator, a comparison operator for your data for your class. So essentially, you can compare two elements of the class and say one comes before the other, and that clearly is fine for numbers. It's also even defined for strings, but it may not be fine for something you come up with. Containers are often well used with the algorithm header. We've already used find, but if you look at the algorithm header, you realize there's a hell of a lot more to algorithms than there is. And I would definitely recommend you have a look at the reference, because some of the stuff you may be coding for your final project may already be available. And we don't ask you to reinvent the wheel, we ask you to write a smart code. So if somebody's already written an algorithm that does it, you might as well use the algorithm. And there are some pretty powerful and useful tools in there. Now, one thing I haven't discussed, but many of you will already run into, is the idea of using exceptions. Exception handling or error handling is the real idea is that you detect and handle an exception which is really a runtime error situation you did not expect to happen or it should not have happened, and essentially is a key part of writing any program. Now, it's crucially important when using dynamic memory management, but it's definitely important in other cases as well. And if you have mission critical software, you really want to make sure that if something goes wrong, you deal with it right. And not necessarily that your code dies, right? Essentially, if it's a hard monitor, you don't want this thing to die, you want the thing to reset to a safe state. C++ provides a neat method for this, which is the try, throw, and catch. Those three keywords go together. So the try keyword is used to look for exceptions, and catch is to decide what to do with them. So you put a piece of code where an exception might occur inside a try, and then at the end of that code, you put a catch statement, and in this case I assume that the error that will be thrown is an integer, and I catch it over here, I work out what the integer is, so this almost looks like a function, and we can decide what action to take depending on what error flag is. And what I would put inside this piece of code over there, I can put a statement if error, then throw my error flag. I haven't defined my error flag, of course, but it could be whatever it is. And essentially, you may be able to deal with that. Now, some of you may already have encountered the no except keyword, which essentially says that something can't throw an exception. If I remember right, Visual Studio requires you to implement it on move constructors and move assignment operators. So essentially the no except keyword really means this code cannot throw an exception. This is called throwing an exception over here. So that's a clear statement that you don't have to worry about that. There are places where you don't want it to happen because the compiler, the code couldn't deal with it at that place. So look at an example over here. Okay, I've got a function divide, which divides two numbers. But I want to protect it against x equals 0. So I calculate y over x. So clearly dividing by 0 is not a good new idea. I've got a divide flag over here. Then I've got defined two integers. I do this thing, and of course that will be perfectly fine. Now I reset x to 0. And if I then divide x by y again, I should hopefully get an error message. And at the end of the try block, I've got a catch. If there's an error flag, I test whether the error flag is divide flag. And I say standard error. I just write to the error output. Error divide by 0. I could even told you what the numbers are in principle. They should be available. An exit with an error flag. In this case, I don't want to recover, but I could, for example, just continue divide by 0. Essentially, right? I can live with that. Let the code continue to where I was before. So, and that would just output y equals x, and then it would throw an exception. You can have multiple catch statements. Suppose if there's more than one type of error, I could have an error flag, I could have an exception double, where the appropriate one will be called based on the type that is thrown. So if I throw an integer, it would catch the first one. If I throw a double, it would catch the other one. And if you have multiple throws, you may well want to implement a catch for every single option, or even a default one. There's a default one, there's a catch with 3 dots in there, which allows you to catch anything. When an exception is thrown, the program exits the try construct, everything within there is reset. If throwing an object is an object instantiated from a derived class, catch the derived class before the base class. Otherwise, can be caught by a base class catch statement, right? Essentially, this is essentially the same thing like base class pointers. You can also have a base class exception. That's perfectly fine. So this order over here is wrong. It should be derived class before a base class, if that's what you want to do. You are definitely advised, strongly advised, and more than encouraged that you use exception handling when allocating memory. If this fails, an exception will be thrown of type bad alloc. So for example, if you do a thing over here, I've got a double myArray. I try myArray is new double with one with lots of zeros. My computer definitely does not have that much memory. So at that point, I would get a memfail, and I could just say standard CR memory allocation failure, return 1. That makes a lot of sense. I can delete my array even though it's a null pointer. I mean that would be fine. By this point, it's out of the code anyway, so this will get only executed if the memory is allocated. Another thing is that pointers are a great cause for problems. And there's a replacement for a pointer which actually is the recommendation. The recommendation is that you're never going to use raw pointers as we've used them up to now, apart from in some very small contexts. Smart pointers are actually crucial if you use the RAII, which is short for Resource Acquisition is Initialization Program idiom. The main goal of this idiom is to ensure that resource acquisition, right, when essentially allocating memory, recurs at the same time the object is initialized so that all resources for the object are created and made ready in one line of code. In practical terms, the main principle of that is to give ownership of an allocated resource, for example, dynamically allocated memory or system object handles, to an L-value object whose destructor contains the code to delete or free the resource and also execute any associated cleanup code. So that's a really neat piece of design. In most cases, when you initialize a raw pointer or resource handle to point to an actual resource, you can actually pass the pointer to a smart pointer immediately. In modern C++, raw pointers should only be used in small blocks of code of limited scope, loops or helper functions where the performance is critical and there's no chance of confusion about ownership. So in your final project, I would like to see no raw pointers, unless they never leave a small scope, right? Otherwise, always use the smart pointers. So what are they? Well, there's 3 different ones of them. There's a unique pointer, there's a shared pointer, and there's a weak pointer. Unique pointer allows exactly one owner of the underlying pointer, which is the most common thing I expect to see. Use this as the default choice unless you know for certain that you require a shared pointer. So shared pointer should only be used when unique pointer is not the correct option, not the other way around. Can be moved to a new owner, but can't be copied or shared. So that's the useful part of that. Replaces the older syntax auto pointer, which some of you may see in some code, which is now deprecated. Unique pointer is small and efficient. The size is 1 pointer and supports R-value references for fast insertions and retrieval from STL collections. So it's a very useful, well-implemented piece of code. Now there's a shared pointer, which reference counted smart pointer, as we have implemented ourselves early in the course, right? We did that. So use when you want to assign one raw pointer to multiple owners, but it knows how many other owners there are, so the information can only get deleted one. The raw pointer is not deleted until all shared pointed opers have gone out of scope or have otherwise given up ownership. Then there's one backup which actually should not be used too often, but can be kind of useful to deal with some edge cases. Actually, it's required for a set of circular pointers. You need one weak pointer in that case. So you've got an object pointing an object, pointing an object, and finally pointing back to the first object. Then one of those links needs to be a weak pointer. A weak pointer provides access to an object that is owned by one or more shared pointed instances, but does not participate in the reference counting. Right? So this is a very dangerous thing to use because you don't necessarily know where the objects still exist. But it's very useful when you want to observe an object, but do not require it to remain alive, to remain in memory. Required in some cases to break circular references between shared pointer instances. That just doesn't work. Circular references are slightly annoying. So that was what I had to say about weak pointers. You may want to look up a little bit more, but the syntax is not the hardest possible. It's quite useful to use. There's something else, lambda functions or lambda closures, and there's some pretty good discussions. There's a really nice discussion over here, which was for C++ 11, but is still good. What I'll discuss here is the basic lambda. The idea of a lambda has been extended from C++ 11, which is typically what I discuss here, to about C++ 20, whereas 14, 17, and 20 over there's substantial additions to it. I'm not discussing most of those additions over here because I really want to get you to the basics. So I've got, for example, a vector. I add some elements to a vector, and I've got an even count over here, and I use something called for each, which I'll explain in a minute, but it goes from beginning to end, and then uses a rather weird object over here, which is called a lambda function over there, which actually I'll discuss how it works, but essentially it takes even count as a reference. It takes int n as an argument, so it's got access to even count by reference, so it can change it and see it. And then it puts output n, which is the argument. If n is even, n percent 2 equals 0, it means the object is even, then I can put output even. I include even count, that's why I needed even count, and else standard cout is odd and close of that. So this has an argument. It also takes this function, has a side effect by modifying this argument over here. And this way I can actually print a count of the even number. So I can iterate over the whole object over here, which is what the for each does. It goes from the beginning to the end. It applies this function to every argument. and essentially at the end I know exactly how many even numbers there are. So this is a pretty elegant piece of code to do that counting. There's other ways of doing this as well within the algorithm class, but this is if you do it yourself. The code uses the for each syntax, which can also be found in the algorithm header. It applies a function to each argument between begin and end, which are the first two arguments. The lambda function definition is on line 15, right? Essentially had the square bracket, which is starts off, and even count, so it's an anonymous function, it's unnamed at the moment. The square bracket part says it has a reference access to even count. I can see it changes value. The parenthesis part shows that it can take an integer as an argument, and then we've got some function body. There are alternatives to this, which is using functors. Well, if you ever want to see how complicated a functor is, you go to the Stack Overflow article, which discusses it. It's so much more complicated that I don't want to do it. Actually, lambdas have other things uses as well, so they're quite useful. The takeaway message is that Lambda and the standard library allow for very powerful programming. The important part is what and how variables are captured, made available within the square bracket. Square bracket with nothing captures nothing. Square bracket with a single ampersand capture any variable used by the reference, so we don't have to specify. Equals capture any variable used by value. Equals, comma, ampersand x capture any variable used by value apart from x, which can be captured by reference, and x capture x by value but don't capture anything else. The return type of a lambda is void by default. So if you don't tell what the return type is, for a simple return, the compiler will work out what the return type is. So return 1, it returns an integer, or you can also use the return value syntax where I use an arrow notation double. So this says it returns a double, and then if I return 1, it will actually return 1 cast as a double. Okay, that's what I got to say about lambdas. There's much more to say about lambdas, don't worry, essentially, but it's up to you to read up on some of these advanced features. So at the end of the course, there's a couple of more remarks I want to make. In this course, you were really introduced, and I really mean introduced, to the main concept of object-oriented programming. The key concepts I really want you to take away from over here, which essentially is the stuff I really want to see in your final code, is the use of classes, which are the rules, and objects, which are the instances. Encapsulation, we control how about data are used. Inheritance, creating class superstructures. Polymorphism, one interface, multiple methods. Class and function templates, structures with generic types. Organizing code, multiple bytes, headers, and namespaces, all used perfectly well with header guards and all the other stuff. And good practice, limited commenting, handling exceptions, using the house style carefully, and if the house style doesn't state it, going back to the basic style that this is based on, and look at that. Our house style is just one of the many house styles, but it's a useful one. C++ is just the beginning, right? Essentially, if you really want to become a coder, there's other languages, Java, C#, Python, Ruby, that all use object-oriented programming. It's not the only one. There's other languages that are strongly based on C++, Rust or Golang as it's sometimes called, are languages, but they don't all use inheritance. Standard C++ 17, which is the version I've been trying to work towards in this course, has been around for almost 3 years. Most, if not all, of its new features are already in the latest compilers, and C++ 20 is definitely not implemented, but we know what's going to happen. And after that, there will be C++ 23, etc., etc. Now, I haven't covered everything, so the best way to code well is practice and try to see sharing code with other people and trying to see how it works. So I really, really look forward to seeing your projects. Thank you very much.